Okay, we're going to start talking about gravity, and I know we've talked about this a little bit in class, but we've been so sporadic with our attendance because of events. Let's just talk about two atoms. So there's an atom, and there's an atom, and I draw my atoms as little clouds of goo because actually that's kind of what they look like. If you talk about all the protons, electrons, and neutrons in this atom, and all the protons, neutrons, and electrons in this atom, they are attracted to one another. Okay? So now we talk about millions and millions and millions and millions, and I'll just make dots of atoms all over this area, and they are forming a baseball. So we look at the baseball on a whole. Okay, when we look at a baseball, every atom in that baseball is attracted to every other atom in that baseball. Okay, since most of the atoms are similar in composition, they're not all the same, but they're similar. Most of the ball has an equal and uniform attraction between all the particles within it. Now here's the other thing that I want you to think about. This ball is also a piece of mass, so it's attracted to every other piece of mass in the universe. And fortunately, we have an equation. And if we talk about that equation, the force due to gravity is equal to big G, and this is the universal gravitational constant. Newton didn't know about the gravitational constant. That was actually Cavendish that came up with that. But it has a value. And what this equation says is that for any masses, and this could be the moon and the earth, it could be a baseball in your toothbrush, it could be Jupiter and the sun, it could be whatever pieces of mass that we have, the force of gravity acting between them is equal to G, which is 6.67 times 10 to the negative 11th times the mass of one object, the mass of the other object, and how far they are apart. So when we talk about the Earth, okay, here's Florida, there's the Earth, here's Asia, here is South America, it goes like this, here's Africa. I know that looks like the Earth. It's perfect. Okay? So, if we look at the Earth has a mass of, and we use 6 times 10 to the 24th kilograms. And for the radius from the center to the edge of the Earth, so if you're standing on the Earth, obviously you're the radius away, we use 6.4 times 10 to the 6 kilograms. So these are the pertinent numbers that we all use a lot in the problems that we end up doing. Talk just a little bit about weight. We know that weight is the force of gravity and its mass of an object times g. Well, if we look at this equation and we say this, mass of the object, mass of the Earth, divided by d squared, and we substitute this in for F, and we solve for little g, or the acceleration due to gravity, we solve for this, the MO's cancel. What this tells us is the mathematical reason all objects fall at the same rate. Because the mass of the object, heavy or light, doesn't even figure into the equation at all. Now let's talk a little about one of the interactions in your book. The Earth is about 80% water, and we have this great big moon. The moon does revolve around the Earth in an orbit, but the center of that orbit is actually about right there. It's about 2/3 from the center of the Earth. So when we talk about the moon, it is actually rotating around this point, not around the center, around that point of the Earth. Okay? And the Earth is actually wandering. If you looked at the Earth, it would actually kind of flip around that point a little bit in its orbit. So now, we look at the Earth, and remember what's on the Earth is water. When the moon is aligned correctly with the Earth tends to do this. It tends to pool water. And remember, the Earth is spinning through this field. So what we end up is twice a day on the coast where there's water, you have tides. And usually you'll have a low tide and a high tide. So you'll have a time when the tide comes in, but or a time when the tide is all the way drawn out, and a time where the tide is very high. And it varies with the period of the month, depending on where the moon is located. So whether the moon, if we looked at the Earth, and this is the moon here, and the sun here, because the sun also affects tides. So if the sun is over here, whoa, that was crazy. So if the sun is over here, there's the sun. If this is the moon, and this is the Earth, that's going to be a whole different scenario than if the sun and the moon and the Earth all line up. This is going to be a different type of tide than this tide, because of the amount of gravity that's pulling on the Earth and the direction and all of those things. So that section in your book about tides we'll have to read. So again, the big piece is this. F equals big G M1 M2 divided by D squared. This one's going to take you a long ways in most of your problems. I have several videos posted for you. I'll have assignments posted for you. Probably taking us out 2 days. We're probably looking at maybe it'll be Thursday before we actually get everybody kind of back together, or we'll check it on Wednesday. Next time I have a full class without anybody disappearing for a very long period of time, we'll get back out of this and we'll do some other stuff. But there's not a lot of labs with this unit, and we just need to get through to where we can solve problems using that equation. So that's it for now.